we were doing eigenvalues and eigenvectors. And I showed this chart before. Here's two different examples of an A matrix. Here we got three distinct eigenvalues, 3, 2, and 1. When that is the case, you are guaranteed to get three linearly independent eigenvectors. One eigenvector associated with each of the eigenvalues. Okay, and they will be linearly independent of each other. You'll only get one per each, one that's linearly independent of others for that eigenvalue. Among all eigenvalues, you get three linearly independent eigenvalues. If you have a repeated eigenvalue, like here, 3, 2, and 2, you don't know if you're going to get 2 or 3 linearly independent eigenvalues until you do further work. And when I taught this, I kind of made it a big deal to know exactly how many linearly independent eigenvectors you get. Like if it's a repeated eigenvalue, it's repeated twice, you don't know if you'll get 1 or 2. If it's repeated 3 times, you don't know if you'll get 1, 2, or 3. You'll always get at least 1. You might not get as many as it's repeated worth. Here, I don't know. We might get 3 linearly independent eigenvectors. We'll get 2 linearly independent eigenvectors for this one repeated root. And we don't know yet. So let's start doing some 3x3 examples, which is also going to lead to more complicated process for finding the eigenvectors. The algebra will be more complicated to find the eigenvalues. So anyway, let's do this matrix. We're going to subtract a lambda off each of the main diagonal terms, like here, and then find this guy's determinant. And it's a 3x3. At least in this case, this first column has 2 zeros in it, so we'll expand by the first column. And I'll just get a 1 minus lambda times the determinant of this lower right part, which will be 2 minus lambda squared minus 1, right? If I expand this out, I get this little quadratic term, which is fairly easily factored. I don't really have to factor a third order polynomial. The whole thing factors like this, and here I get a repeated eigenvalue. One is a repeated eigenvalue, and the other one is 3. So the algebra can get worse. I never made my students factor a cubic. It would be a case like this where it kind of just comes out fairly easily. If it was really hard, I would just tell them it in a hint anyway. So here's the thing. We don't know at this point if we're going to get 1 or 2 linearly independent eigenvectors for this repeated eigenvalue. See what happens. So let's do the distinct one first. This lambda equals 3. Well, we're guaranteed to get 1 out of that. So I'm subtracting 3 from the main diagonal. So I'll have a minus 2, minus 1, minus 1, right? We do Gaussian elimination at this point on the augmented matrix. Multiply, divide by minus 2 here. I get a minus, or a 1, minus 3, 0. Well, I won't go through all that. You can add the bottom two, or add this one to that one, replace this one with it. That. So here it is after Gaussian elimination. And you better always get a row of all zeros at the bottom, at least 1 row of all zeros. If you don't, you did something wrong prior to this. You're not supposed to get, you should always get at least 1 free parameter. There's an infinite number of solutions. That's a check on your work. You better get a row of all zeros. And what does this mean? This means like little k sub 1 minus 3k sub 2 equals 0. And the second equation means k2 minus k3 equals 0. I can pick some whole numbers, and this will satisfy it, right? k1 equals 3, 3 minus 3 equals 0, and the 1 minus 1 equals 0. This satisfies these equations. You have to do a little bit of algebra here, right? Because each of these rows is an equation, corresponds to an equation. Little k's are the elements of the big K vector, or n by 1, in this case 3 by 1 matrix. Now let's do the repeated group, the repeated eigenvalue. Subtracting 1 from the main diagonals, I get a 0, 1, 1, right? And the rest is the same. Here's my augmented matrix. I do a little bit of Gaussian elimination. I get this. Again, a row of all zeros. How many rows of all? This says K2 equals 0. This says K3 equals 0. So I'm left with K1 being free, or just the eigenvector is 1, 0, 0. I only get, and it's only possible to get, one eigenvector for this repeated eigenvalue. So out of this whole problem, I really only get 2 linearly independent eigenvectors, even though it's a 3 by 3. And here's the trick. Once you do the Gaussian elimination for a repeated root, how many free parameters do we have in this matrix? Go back to solving algebraic equations. As many as there are all 0 rows. Here, there's only one. So you only have one free parameter. Let's see what happens in this case. We'll do this the hard way first. Later in the course, there'll be an easier way to do this particular problem. But here, it's a diagonal matrix or triangular matrix. So the eigenvalues are just the main diagonal terms. So 0 is a repeated eigenvalue, and then we have 1. Let's do the 1 first, the distinct one first. Subtracted 1 from the main diagonal terms, so minus 1, 0, and the rest of them stay the same. Here it is after Gaussian elimination. And it says K1 equals 0 and K2 equals 0. So I'm just left with this 0, 0, and I'll call it 1. I could put in any number here, but I like ones if it's possible. So there's one eigenvalue, and it corresponds to lambda equals 3. All right, now let's do the repeated roots. 0, so everything's the same here. Here's the augmented matrix. Gaussian elimination just means move this one up to the top, and there we go. Now look, 2 rows of all zeros. I'm going to get 2 free parameters, which means I'm going to get 2 linearly independent eigenvectors. And now I'm going to do something special here and tricky and not often explained well in textbooks to get those 2 linear independent excuse me, eigenvectors. All this matrix tells us is that K3 equals 0 no matter what. And I do what I call the 1, 0, 0, 1 trick. When I have 2 things to play with, to make sure they're linearly independent, I'll set 1 to 0 in one case and the other to 0 in the other case. In this case, I set K1 to 1 and K2 to 0. So I get 1, 0, 0. And in this case, I set little k1 to 0 and K2 to 1. So I get 2 linearly independent vectors out of this repeated eigenvalue. And I get the total of 3 linearly independent eigenvectors for this 3 by 3 system. The way to go about that is the 1, 0, 0, 1 trick. And the way to know is this final result of your augmented matrix. How many rows of all zeros do you have? Same as the number of free parameters. By the way, any linear combination of these two guys would also be an eigenvector, but it wouldn't be linearly independent of these two guys. And I'll quickly go the one more case. It is possible to have complex eigenvalues. Say this is your matrix. We'll subtract lambda off the main diagonals, -1 minus lambda times 1 minus lambda plus 2. Right? That leads, we'll simplify it, it leads to this quadratic. I get a complex conjugate pair of eigenvalues. And as long as the A is all real, your eigenvalues will come in, your complex ones will come in complex conjugate pairs. So then subtract that. Now that we've done that, we find the eigenvectors. And once you find one eigenvector, the other eigenvector will just be its complex conjugate. Both eigenvalues and eigenvectors come in complex conjugate pairs. So let's do it just like we did when it wasn't complex. We have -1 minus, and I'll pick the plus. So -1 minus I3. 1 minus I3. The off-diagonal terms stay the same. And by the little time-saving trick I had before, I have 2 over minus this. 2 over 1 plus I3. And then K2, the other eigenvector, will just be this guy's complex conjugate. If I'd use the bottom row in my little time-saving trick, I'd have this guy on the right on top, and this guy's negative on the bottom. So even though these two different sets of answers look different, they're the same. They're a scalar multiple of each other, where scalar can mean complex number here. So that's how you do complex. All right, that's it. We'll get to diagonalization. 1001 trick. That was the little nuance thing. Good to know.